Okay, looks like we've got our first batch of guests in, and some others will be joining us in a minute. Welcome to the faculty roundtable for the Ming Hsieh Department of Electrical and Computer Engineering. My name is Paul Ledesma. I'm the Director of Undergraduate Admission here at the USC Viterbi School, and we have three fantastic faculty members here that are here to share their experiences and talk a little bit about, to you about their department, about their backgrounds. I'm going to have them introduce themselves. We'll first start with Dr. Mitra, then we'll go to Dr. Sideris, then we'll go to Dr. Nayak.
Great. Well, it's great to see you all. Thank you so much for joining us. I'm very excited about this opportunity to talk to you about our department. Let me tell you a little bit about myself. I've been at USC for about 20 years. This is actually my second job. My first faculty job was at The Ohio State University. So I have a little bit of perspective between a very, very large state school and what I'll call a medium-sized private school. I do research in wireless communications, although these days, it's a little more than just your cell phone. Things have really evolved. So I also have projects with colleagues who do work in robotics. I have a nice new project with colleagues in microbiology, where we're using some of the strategies and mathematical models that we have for describing large wireless networks to describe large microbial communities of bacteria. So that's a little bit about me.
Great, thank you. Dr. Sideris.
Hello, everyone. I have been at USC for a lot less time than Ubli has. I've been at USC since August 2018. I'm an assistant professor of electrical and computer engineering. Actually, I consider USC as a big school because from my background, I did both my undergraduate and graduate degrees at Caltech, which is actually down the street. It's fairly close by, but it's a tiny school. And so I've been used to a small school environment the whole time. But I really enjoy actually how big, broad, and diverse USC is. My research areas are in integrated circuits and photonics and computational electromagnetics for primarily biomedical and wireless applications. So we work on a lot of hardware applications. We design circuits, we design computer chips, and the application areas that we're mostly interested in either relate to as Ubli mentioned, wireless communications, such as cellular applications, for example, how we can communicate more efficiently with each other, and also biomedical applications. And so what I mean by that are biosensing, point of care devices, ways that you can diagnose diseases, which I guess today is becoming very relevant in the situation that we're in, and designing chips and biosensors that can be very inexpensive and hope to one day bring healthcare and diagnostics to the comfort of the user's home rather than in a laboratory setting or in a doctor's office. So yeah, that's a little bit about myself.
Thank you so much. And Dr. Nayak.
Hi, nice to meet everybody. My name is Krishna Nayak, and I'm also very excited to be on this panel and answer students' questions and new students' questions. I'm originally from Florida, Tallahassee, Florida, and I did my undergrad at Florida State University, and then I did my master's and PhD at Stanford, and I've been at USC as a faculty member since 2003, and I've had a great time here, enjoy working with students, enjoy our academic environment and our research environment. My particular research area is magnetic resonance imaging. So I work on designing algorithms that MRI scanners use to create beautiful and informative images for clinicians and also for basic scientists that are studying how the human body works. And I also teach undergraduate and graduate courses. Undergraduate courses, I teach the freshman academy class sometimes. I teach undergraduate linear systems, and in the graduate work, in graduate courses, I teach some digital signal processing classes and MRI medical imaging classes.
All right, very cool. And in full disclosure, both Krishna and I, it's oddly enough, one of my high school friends became one of his grad school buddies, which is really weird. And we found that out recently. So I always like to share that. And you can listen to Krishna's podcast episode to get into the full details of that. But that's not about today. What we're going to talk about is the Department of Electrical and Computer Engineering. And how we're gonna run this session is I'll start this conversation going. We'll talk about the department, the discipline, the curriculum, and then as we get to the end, I'll open up the chat for all of our guests to start asking questions. So please don't use the chat right now if you just wouldn't mind listening and participating, but think about those questions and have those ready at the end. The first question I'm going to ask to the panel, and whoever would like to take it, is seemingly a simple question, but has a definite complex and varied sets of responses. What is electrical and computer engineering? I know it's broad. I know it is diverse. So I'm going to just throw that out to you all and see who takes it.
So I'm going to start things off as the old person on the panel. But I'm going to say the following, which I actually truly believe. I do think it's one of the coolest forms of engineering. It spans everything from deep mathematics and theory to very applied systems where people are trying to optimize the design of computers and chips, and Constantine can tell you more about that. I like to use cell phones as sort of an explainer of different parts of electrical and computer engineering. But to be honest, there are lots of parts of these cell phones I don't understand how they work. So it's a very diverse discipline. The kinds of things that I do have to do with how we describe signals that are transmitted between, the base station, if you will, and your cell phone. And what we try to do is undo all of the distortion and errors that are introduced in that communication. We worry about how many different users can share this resource, like the radio resource. We wonder about fundamental limits, like what's the most amount of information that you can transmit between a cell phone and a base station. So I do a lot of applied mathematics, a lot of probability, a lot of linear algebra. These are some of the basic tools that we use. I am very interested in, like I said, fundamental limits. What's the best that we can do? And then hopefully design signaling strategies and algorithms that allow us to get close to that. Even though I personally do a lot of theory, I try to work hard. I work a lot with people who are what I would call data generators. So for example, with those biophysics colleagues, they're generating experiments that give us measurements of the signals that bacteria create. I've worked with colleagues that have built wireless body area sensing networks where we take the signals off of the different sensors and manipulate them to make inferences about what people are doing. I've done work in underwater acoustic communication where I have colleagues that have built underwater acoustic modems, and we get the received signals from their transceivers and we try to manipulate them. So for me, it's detection, estimation, inference, learning. A lot of the data science that's going on these days has electrical and computer engineering aspect to it as well. So that's kind of my piece of it, the sort of system side of things.
I guess I can go next. So I think that what's so amazing or beautiful about electrical engineering is how broad it really is and how broad it's become. And so my research area probably couldn't be more, on the face of it, be more different than Ubli's. I work in hardware, so we design integrated circuits, we design chips, we design printed circuit boards. So my area is probably in some ways what electrical engineering more traditionally started out as, is doing hardware. However, nowadays it's become so broad that topics that you might think are computer science or applied math, as Ubli mentioned, or applied physics, or many other disciplines, even bioengineering, can easily fall under the umbrella of electrical engineering. And our department is actually extremely interdisciplinary. And as you'll find out based on the different projects that we work on, and if you go to the USC website or to a lot of our colleagues' websites, you'll see that all of the areas that they work in, most of the time, they don't actually just work in one small sort of subset of an area. They actually have quite broad applications and interests. And I think the primary reason for that is because in order to make research progress in the world today, to solve these remaining problems, these huge research problems, we need to be interdisciplinary. We need to be able to cross boundaries between just being like, I'm only a circuits person, or I'm only a math person, or I'm only a computer science person. And electrical engineering, I think, is one of the majors that has really managed to embrace that and be able to kind of unify or be an umbrella for many different sub areas. And so I think that a lot of people, for example, a lot of our colleagues in our department primarily do software programming, and somebody that doesn't know might think, oh man, this should be computer science, but it really actually falls under electrical engineering. And so I don't know if I exactly answered what electrical engineering is per se, because it's so many different things. And I think the cell phone example is wonderful because, for example, someone like myself would work on the actual hardware that makes a cell phone, the actual chips and the printed circuit boards and the antennas and all those components, versus somebody like Ubli, as she mentioned, actually works on the communication algorithms and the mathematics of, how do you encode the data to communicate efficiently. And I think with that, I should probably pass it on to Krishna.
So, but if I can interrupt just before Krishna speaks, the other point I wanted to offer in terms of the diversity, but also the collaborative nature. So Constantine and I are talking about joint projects, and I'm trying to understand how the sensors and systems he builds, what their constraints are, and how that should affect the algorithms that we design. And so we're looking at some really interesting strategies for kind of doing in-body sensing, both from a circuit point of view and a sensor point of view, as well as an algorithm point of view. So, sorry, Krishna, your turn.
All right, thanks. So I think in some ways it's easier to answer questions like what is engineering, because actually all of the different engineering disciplines have a lot in common. We imagine things, design them, build them, debug them, and in general, all of the engineering disciplines really create a lot of value because we're creating new technologies and new realizations of existing technologies. And I think what Ubli and Constantine did by raising examples is the best way to capture what electrical engineering is. It just, our discipline really contains all of the necessary toolkits to engineer a wide range of devices and things that we are going to use in the future. The cell phone example is one, wearable sensors is another. In my own field, almost all medical instrumentation, right? Medical imaging instrumentation. People often think of those as biomedical engineering, but if you go down to actually what the instrument's doing, when the rubber hits the road, it's something that involves electromagnetic fields interacting with the human body. It's something that involves a circuit. It's something that involves an algorithm for estimating something about the body from these measurements. And all of these things really come together in electrical and computer engineering. And you have a little bit of a biased sample with 3 ECE faculty on this call, but this is definitely what drew me into this discipline, the fact that you can learn all of the necessary tools to bring to fruition a wide range of technologies like cell phones, like wearable sensors, and like medical imaging instruments.
Also, Krishna is never going to say this because he's super modest, but if you get an MRI, it's possible that one of the sequences in that MRI machine was designed by his team. So he works very closely with MRI manufacturers to help translate this cutting edge research into systems that help all of us on a daily basis. So I find this super impressive about him.
Absolutely. Absolutely. Now, thank you for that. And I think that's what's so interesting, is that electrical engineering is so diverse and that there's not one definition. So I think that definitely helps shed some light on it. Can we talk a little bit more about the curriculum and what students can come to expect for their undergraduate curriculum, maybe how it gets started and where it leads? Because it definitely starts with, digital logic kind of moves through circuitry, but can you help shed some light on that?
I think Krishna should start this one and then I can follow up.
You got it.
Yeah, so the undergrad curriculum, over the last few years, we've been trying to get in first-year students engaged in our discipline more directly. I'd say about 3 or 4 years ago, it was only like maybe late sophomore year, early junior year that you started taking, serious EE classes. The curriculum has changed more recently. So in your first semester, you actually are dealing with some real data, might be doing a programming class. We have a linear algebra class that's offered in the first year or early in the second year. So we actually do much more discipline-specific engagement in the first 2 years. You also have the opportunity to do a little bit of a specialization in the later parts of your undergrad. So we have different tracks. There's like a systems track and a few other tracks. And that slightly changes the electives that you might take in your junior and senior year. And also we have capstone design courses. So you'll be taking on one or more classes where you actually design and build something new. I'm actually working on a candidate new capstone course that might, if it comes to fruition, it should be ready by the time this incoming class is in their junior year, where groups of students will build their own little MRI scanner from scratch. It's about as big enough to scan your finger, but we're hoping to make that happen by the time you guys are juniors.
A little doll-sized MRI.
Right.
Basically, yeah.
So following up on what Krishna said, the three sub areas that we have are systems, and Krishna and I are in that area. There's also computer engineering. And I guess it's hard to say, Constantine, if you were more in computer engineering or in electrophysics. But these are sort of the different sub-disciplines. And so, for example, in some aspects of electrophysics, you might look at antenna design or more advanced optics. We have colleagues in electrophysics that build solar cells, RF circuits, that kind of thing. And computer engineering can be everything from more circuit-related design to more system design, like how do you design or optimize the operating system? And again, I keep going back to cell phones because this is the one aspect that I understand, not because I do computer engineering, but we had a multidisciplinary project on wireless body area sensing. And from my conversations with my computer engineering colleague who was on the team, I understood that these were the subsystems that they were optimizing, which was power use on the cell phone, sending it to different subsystems so that we could be power efficient in assessing human behavior. So those are the different sub areas. I personally have taught Freshman Academy, as Krishna mentioned, which is a gateway course, if you will. It's actually, usually it has a variety of engineering discipline students in there. There's also an intro to electrical engineering course that you can take. Linear algebra, one of the reasons why we moved it to the first year is because of the power and the utility of the things that you can do with it. So as an example, if any of you know anything about OFDM or Wi-Fi, linear algebra gives you the tools to actually understand that signaling mechanism. Or if you think about how the first search engines were, PageRank is based on properties of matrices in linear algebra. And so in fact, when I've taught linear algebra, I've taught PageRank as one of the applications of some of the tools that you're learning there. A lot of computer vision relies on these linear algebraic tools as well. So it's a very powerful first class that actually allows you to do things right away.
Actually, linear algebra is also extremely important for computational electromagnetics. So it's, I think, linear algebra and differential equations are probably I would say, the most useful classes in terms of electrical engineering and things you'll learn later on. I don't, were you done, Ubli? I didn't mean to cut you off.
Oh, no, go ahead.
Okay. So I think Ubli and Krishna covered the curriculum quite well. I teach linear circuits. It's a sophomore level class. It's basically the introduction to circuits, to analog circuitry. And it's actually, it's a really fun class. And I never had the opportunity to have a class like this when I was doing my undergrad. The classroom is actually, it's actually a lab itself. And so the classroom at each desk or each station, there is a full setup with an oscilloscope, power supplies, voltmeters, you have breadboards. And so during the class, actually, when we're teaching you different concepts and topics, you actually get to build these circuits live in real time and see them working and see that it actually is not just something virtual on a marker board or a whiteboard or a PowerPoint slide, but you can actually build what we're learning and see that it actually, these circuits work, and that the theory that we're developing to describe how they work actually applies. And at the end of the class, there's a project where where the class actually gets to build from scratch their own guitar amplifier, and also filter. You build filter circuitry, and you can. The project changed a little bit each year, but this is what it was last year. And they build filtering circuitry, so you can actually tune. You can use it to tune your guitar or tune for specific strings or chords. So it's actually a really fun class. It's the very first circuits class. And actually, it's also required for biomedical engineering. So we actually have a pretty broad and diverse group of students that takes this course.
That was great. Can we go off of that for a quick second? There's some words that were thrown out there that I want to dive in a little bit more, specifically linear algebra and the ideas of math and science and how that changes into engineering. If we keep in mind, we have high school students here where they've taken math classes, they've taken science classes, and when you talk about taking a linear algebra class, is that just a math class, or can we talk a little more about how that's integrated into the curriculum and how that's taught by the department?
So you raise an interesting question, because when I taught linear algebra, I was tempted to give a project to the students, which was to interview faculty in ECE, ask them if they could without using linear algebra. And I was convinced that the answer would be no, because you know, matrices and vectors are just visual representations for us. So I was hoping that we could create this movie, like, you know, trying to live a day without linear algebra, because my contention was that it was going to be impossible. So I can't speak for the others, because I mean, truly for the research that happens in my group, everything is matrices and vectors and eigenvalues and eigendecompositions and looking at asymptotic behavior of systems, you know, that evolve using plants and controls that are described by algebra and state spaces. So actually, tell me, do you want us to know what linear algebra is? Or, I mean, to me, my research is linear algebra and probability theory. It's complicated versions of that, but the basis of what we do is based on these courses that you actually will get an undergraduate. And then if you go into school, we give you a much more intense advanced version of it. And then if you want to keep going, there are even more intense and advanced versions offered both within ECE as well as in the mathematics department. And my graduate students do take those, you know, even more linear algebra and courses. So I think these are the basis of a lot of what we do.
Yeah, that's great. I think maybe I didn't phrase my question. That was fantastic. I'm not phrasing my questions well. What's the biggest difference between math and engineering? Because I think our students love math. They don't know what engineering is yet.
So I always think of engineers as problem solvers. And so I find that some of my colleagues in mathematics are interested in properties or features of problems, but may not be as worried about whether they solve something in reality. And for us, that's always the distinction. Like, you know, how does this description of a system relate to an actual system? We do simplify things and abstract them, but in the end, for me, if it doesn't work, you know, again, on real data, which is one of the reasons why my research group, even though we're theorists, we always try to work with data generators. Oftentimes what we see is that the theory is very robust and actually does work in the real world. So for us, the starting point is always, what is the specific problem that we're trying to solve? And then the math is there to support and help us figure out the solutions. And sometimes the math, you know, the real world is so hard that the actual mathematical description is not useful, right? So then you have to go back and ask yourself, well, what can I learn from the idealized version of the problem? How do I have to change things? But it's ultimately trying to solve a problem. How do we do things more accurate, faster, with less power, or even less expensive? That's a big deal now too, which is designing solve systems that are easy to implement and may use systems or circuits, you know, like accelerometers or GPS that are cheap and therefore not, and can use signal processing and communication theories that the hardware may not be as accurate as we would like it to be, because we want it to be cheap, low power.
Let me just, I also completely agree with Ubli. I want to make a little distinction though. You know, in addition to math, we also rely on almost all of the basic sciences, right? So, you know, we in a quest to build something, or to create some new capability, or to fulfill an unmet need, right? Which is what engineers are typically focused on. We often have to go back to fundamentals, mathematics, physics, things like that. And so it's natural, and also I think very important to have a love and joy for mathematics and physics and things like that. That'll help you immensely as you go on and actually
I like
are
to think
a practical problem solver.
Those things, right? We're harnessing elements of the real world that are described by scientific. So I like to think of scientists as trying to explain the world, whereas at the risk of saying something too extreme, but control the world, right? So we're trying to harness the natural environment, harness electricity, etc., solve problems that hopefully make the world a better place.
Yeah, as engineers, I was going to say, as engineers, we try to build things, and in order to be able to build things to solve problems, you need to actually understand how the world works. And so we rely on, as Krishna and Ubli said, basic science, mathematics, physics, biology, because without these sciences, we wouldn't have an understanding of how all of these fundamentals work. And if you don't have an understanding, you can't really effectively build new things or create or contribute new things to society besides potentially tinkering. But and some of engineering actually does end up being tinkering sometimes, I guess. There is trial and error. But in terms of the research process, we always try to break something down and understand how it works at the most fundamental level, and then build something new back up again. And I think that's a distinction, is that we don't stop at understanding something or understanding how something that exists already works. We try to create something new.
And in light of that, in each of those answers, you all brought up doing something new, solving some sort of problem, building something, creating a new capability. And I think that leads me to research. You've all touched on your research slightly, but can you each talk about what you're doing in your research, and where you see that going, where you see that leading at the end use? So maybe Krishna, we want to start with you, and then we'll work our way back.
Sure. I'll just give a couple of examples. So one of my group's projects is to develop a new diagnostic test for coronary artery disease, which is a leading cause of death in the Western world. It's heart attacks, right? So we have developed and are improving a test that is safe in patients that have kidney failure. So basically, this is a project that's motivated by a major unmet need in society. Society has rising rates of chronic kidney disease and kidney failure. And right now, there's no good diagnostic test for monitoring their heart status. And so we came up with a cool idea that's based on magnetic resonance imaging. And it required developing some special electromagnetic pulses and pulse timings and some algorithms for making maps of blood flow in the human body. And then, my team is kind of building prototypes, running them on the hospital MRI scanners, testing them in volunteers, testing them in animal models of disease, and testing them in patients next year. And if it works, this could be the next standard of care test for patients with kidney failure. This is like one example of a research problem that my lab is working on. Another example that we've just started working on is how to make diagnostic technology more accessible. Testing like MRI, it's not available in rural America. It's not available in a lot of countries that are under-resourced. And so we've come up with some clever ideas, I think they're clever, for how to reduce some of the cost of the system and compensate for it with modern computational methods for improving image quality. So we got a grant to install a new MRI scanner in the Mickelson building, which is on the main campus. It's going in August, and it's going to be operated at a very low field strength, which is more easy to site and should eventually be cheaper to manufacture if a big company decides to take this project on. And we're going to spend the next several years trying to make modern MRI capability work on this type of instrument, which could improve access to the improved healthcare you get with MRI. So these are just a couple of examples of some of the research problems. Is that what you were getting at, Paul?
Yeah, that's great.
So a couple of examples.
Constantine, you want to go next?
Sure. So I can give a couple examples as well. So on the bioelectronic side of things, one area that we are very much interested in are point of care biosensors. And so what I mean by that is what we're trying to do is actually very, very similar in spirit to what Krishna mentioned, is trying to make healthcare more affordable, trying to bring it closer to people rather than the current modality for doing diagnostics is essentially, as I'm sure you're all well familiar with, you go to the doctor's office, you get blood drawn in many test tubes, they take a lot of blood, they have to preserve it, ship it off to a centralized lab-based facility where they do the analysis, and if you're lucky, maybe a few days later you get the result. Sometimes if it's a more complicated test or if they're backed up, it might take a couple of weeks. And then the doctor needs to call you and tell you, explain the results and everything. And so what we're trying to do is we're trying to miniaturize these diagnostics, this equipment that right now takes whole labs worth of space and is costs multiple millions of dollars. And we're trying to miniaturize them and make them cheap. And by cheap, I mean that each diagnostic sensor should cost less than $1 and only require, for example, a small sample, like a tiny drop of blood or a nasal swab or a drop of saliva, and be able to eventually to deploy these either in the field for underdeveloped countries or even in people's homes, and so that people can test themselves. I think the two major causes of death in the US and in many other countries are heart disease and cancer. And both of these are diseases that, if caught early, the prognosis is a lot better and they're a lot more treatable. And so, for example, heart disease, many times somebody may have a heart attack or a stroke, and they might have no previous history or knowledge that they have heart issues or a heart condition. And in those situations, it might be too late. However, there are diagnostic markers in the blood that can determine whether there's inflammation or whether there's, so cholesterol, for example, is one that we all know of. And being able to track these and being able to measure and determine somebody's health before it becomes an issue, before you feel that something's wrong. And so, for example, cancer is another one where many times when somebody gets to the point where they feel that something is physically wrong and they go to the doctor, the disease might have advanced to a point where it's too late. And it might be, with current existing medical technology and medicine, it might be too late to have a good outcome. Whereas if you can catch it before it becomes a tumor, before it becomes, it spreads to the rest of the body, then the chance for survival is a lot higher. And so I think being able to move a lot of this technology into people's homes and make it easy to use and as non-invasive as possible allows people to now check themselves and test themselves, even when they don't feel that something is wrong. Maybe they can just, check themselves once a month or something like that, rather than only going to the doctor when they feel that something is wrong and having to have diagnostics and blood work. And so what we work on are designing chips that are biosensors, that are these tiny little devices that you basically are so small, they're millimeter size, and you basically need a microscope to be able to look at them. And they take tiny samples of DNA or proteins or cells, biomolecules that you would find in the blood, and can do analysis and detection and quantify whether some specific disease or virus or whatever you might be looking for is present. And so that's one application that we work on. On the computational electromagnetic side of things, we actually try to design this. So this is very different. It's shifting gears a little bit. So this is a lot more math, and this is where the knowledge of linear algebra and differential equations comes in. But we come up with computer algorithms and computer software that the idea is that we can tell the algorithm to design new electromagnetic devices such as antennas for us. And so many times an engineer knows the specifications that they want for an electromagnetic device such as an antenna. They know that they want it to have a certain amount of efficiency, maybe a certain amount of communication bandwidth, which has to do with how much data you can send at a certain point in a certain amount of time. But going from the specifications that you need to an actual physical device that supports these specifications is a different story. It's a really difficult problem. And countless hours are spent by engineers often knowing what they want and trying to achieve it in terms of developing a device that can do this. And so our research and our projects in computational electromagnetic center around coming up with algorithms that can build, given these specifications, can automatically build or design these devices for you, these structures, that then the engineer can then take and fabricate them, and they should perform in the way that you would expect, that you ask, in the way that you ask the algorithm to design a device for you. So those are kind of two different projects that we're interested in and work on in different application areas in engineering.
Great. So when I got my PhD, which was in 1994, and people would talk about communications and trying to do novel wireless communications, the focus was really on what we call point-to-point, one transmitter, one receiver. And of course, now things have changed and evolved a lot. And so we're interested in how we design these systems, keeping the entire network into consideration. So how do I design signals that should be transmitted from different cell phones, knowing that they're communicating within a larger network? Because of the complexity of these large wireless systems, we've been looking at the application of these new machine learning techniques for these problems, but trying to do it in such a way that it's not just a black box where we pick our favorite neural network algorithm off the net and we plug in a bunch of inputs and a lot of outputs and see what happens. So we look at optimal design, see if we can identify some properties of these optimal systems, and then use that to more intelligently train and learn for these machine learning strategies. One of the things that we're also looking at is trying to do learning in a distributed fashion where we're trying to maintain the privacy of the signals that are being sent. So you can imagine, as a very toy example, let's say I want to know what all of your average weights are. Now, it might be invading your privacy for me to somehow attach your weight with your name and get all of that data. But is there a way for us to exchange information such that what we're really learning is just the average without providing any identifying information about all of you as individuals? And this is something that is of strong interest as we do more and more of our communication and computation over this wireless infrastructure. And we're trying to use properties and the randomness of wireless channels as a way of introducing some of the security and privacy. The last thing that I'll talk about, which is in a way very topical, but also some of the most mathematical work that we're doing, has to do with this very classical problem called experiment design. So to put things in the context of the current times, lots of people are designing, for example, these serological tests, which are based on blood, to figure out if individuals have the COVID-19 antibodies, trying to understand if the presence of these antibodies then suggests that we have immunity. There are lots of different tests out there of varying quality, expense, et cetera, et cetera. Is there an intelligent way to figure out what might be the series of tests or who should be tested so that we can figure out the antibody makeup, if you will, of a population as fast as possible? So the usual extremes you think about is maybe you have some really cheap test that isn't very accurate, and then you're working your way up to an expensive test that's super accurate. And understanding something about the population of the that we have and statistics of where there might be hotspots of people who have had COVID-19, can we use that information in order to design these testing strategies in a fast way? And one of the ideas that we want to use is actually a really old idea that was used, I want to say in World War I, but might have been World War II, where applying some of these blood tests was kind of expensive. And so at the time, and they were looking for certain kinds of diseases, and they would take blood from all of the soldiers. And the previous strategy was you would apply the test to every single soldier's blood one at a time. So if you had N soldiers, it would take you N tests, but the tests were expensive. So the idea that they came up with was to take the entire group that they wanted to test, break them into two groups and pool their blood and apply one of those tests. And if it was positive for one group, you'd say, okay, now I'm going to take that group and divide it into two again. And so essentially you're doing a form of binary search, and you keep dividing until you figure out who all has the condition. And you go from N tests to log N tests. And if N is big, that's a huge savings. And so again, for some of these serological blood tests, we believe we can come up with smart, what are called group testing ideas that allow us to apply many fewer tests, but hopefully learn much more accurately what's going on in a population of individuals. And I literally just got email today from Dr. Neeraj Sood, who, if you've been following in the press, there are some studies that have been jointly conducted by USC and the LA county health organization, where they've been doing massive amounts of testing in populations to try to get a feeling for what is the actual prevalence of COVID-19 in various populations. And so we're hoping to get access to some of their data to see if we can come up with much smarter ways for them to test many more people more quickly and more accurately. And we have the capability of actually combining tests of different accuracies and coming up with strategies that work well. And if you cared, the asymptotic properties of these methods are actually really good. And we make decisions much more quickly than the state of the art, which are also asymptotically optimal, but we're faster. So this is why we're hoping that this very theoretical piece of work that we've been doing might actually have the possibility for making an impact on assessing the presence of COVID-19 in the population. To be honest, we're probably not going to do anything now, but when this second unfortunate surge probably happens in the fall, when we all start getting sick again, flu season, et cetera, we might be in place to do things much more accurately and efficiently.
Thank you. When you asked about average weight, I just realized whatever it is, I've gone up over the last.
COVID-15, you have it, huh?
COVID-19.
Yeah, I'm working hard on that. All right, so with that, I'm going to open it up to our guests to use the chat and go ahead and ask your questions. So you have these faculty here. I will do my best to moderate those questions. In some situations, those questions tend to be similar, and so I'll blend them together. And sometimes they may be related to the school overall. If they are related to the school overall, I'll maybe give a brief answer, but I'll really push you to our school keynote sessions. We have our last one next Tuesday if you haven't attended that. But go ahead and get your questions into the chat there.
So while people are coming up with questions, I wanted to say one thing about USC in general and the School of Engineering, which is, we all know that you're looking at many different kinds of schools. And again, as someone who was at a very large state school and has some exposure to small schools, because I did my PhD at Princeton, one of the things I love about USC is it kind of has the best of both worlds, right? It has a lot of the amenities that come with having a reasonably sized population in terms of extracurricular activities, the kind of people that come on campus to give talks, research opportunities, et cetera. But within the School of Engineering, especially this undergraduate office that we have, it's a very high touch organization. The staff there get to know all of the undergrads. If you have any kind of challenges or issues, it's easy for you to get help and easy for you to interact with either a staff member or a faculty member in order to resolve your problems or to do something big. And I think that's one of the unique things that we have at USC.
So Jay asked a great question, and I love it. What are some common mistakes that students make and hopefully eventually learn from?
I think I can answer that, at least what my perspective or take on it is. I think the biggest difficulty in transitioning from high school to college is learning to manage your own schedule and having full responsibility of your schedule and where you go, whether you go to a class or whether you don't go to a class. Most classes aren't going to take attendance, and so if there's students that decide to skip classes, and that might actually be quite detrimental because you'll miss out on a lot of important or useful material and it might be difficult to catch up. And that ties in with time management. I think when you're completely free to set your own schedule and do anything that you want, I think a lot of students at the beginning think they have more time than they actually do, and so they might sign up for tons of different activities and clubs and extracurriculars or more classes than they can handle. And I would like to say that almost all students quickly learn from this, and it's sort of like a self-equilibrating sort of thing. And it's just, I guess, being completely responsible for your own schedule and your own activities and classes and how you manage that. I think that's a common thing that students have difficulty in the beginning, but then adapt pretty well to.
So there are some great questions here. I'm actually going to take one that I'm not sure that we have an answer to, which is Aviv's question about how are labs and interactive things going to happen in the fall as we try to figure out how to navigate sort of a post-shelter-in-place universe. So both Professor Nayak and I are on a School of Engineering committee whose goal is to figure out those things exactly. And even though this committee was constituted recently, I just want to let you know that within the Viterbi Research Committee, we've been actively talking about how we're going to have research and lab work happen. So I'm not sure that we have an answer right now, but we are working on strategies to figure this out. And the plan is, you know, in the next couple of months, there will be a series of strategies in place. The goal, of course, is going to keep everyone safe, to make sure that you are learning as best as you can. We'll see if we can figure out what can be done at home versus on campus. Can we create environments on campus where everyone can have appropriate distancing and there'll be appropriate cleaning, et cetera. So I wish I could tell you more than that, but I can tell you with confidence that we are actively working on this.
Yeah, if I can add, I mean, this question has come up at every session we've done, and unfortunately there just isn't an answer as to what are the plans for fall, because we haven't gotten there yet. Right now the university is planning on fall going forward as normal, but we all know things are going to evolve.
Fluid, yeah.
And everybody is planning and working on different scenarios. But if we need to go remote, we will go remote. And it was very successful for the spring semester so far. So the continuation of the educational process has not been paused at all. And we're definitely not stopping. We know that much. Go ahead. I'm sorry, Ubli.
Well, I was also going to say, because of, you know, LA being a city that has a lot of universities, I have a lot of neighbors that teach at a variety of different places. And I have to be honest, I was
in the professor neighborhood, or they are just all
kind of a professor neighborhood. So don't tell anyone. I live very close to UCLA. But I was very proud of the fact that USC got on top of things really quickly. So what the students probably don't know is that we actually did dry runs of online teaching before shelter in place happened, because the university administration realized that this was likely to happen. So we did a lot of testing, and also the School of Engineering. We have this fantastic distance education network that's been around for 40 years. And I, as a faculty member, have been very grateful for having these amazing staff engineers that have been holding our hands through all of this process. Even though I do online teaching regularly, doing it from home is a different experience. And we've just had a lot of help and assistance to make this be as smooth as possible. And if I can do, you know, Trojan versus Bruin little rivalry here, compared to my neighbors, we just had a much better experience because USC had planned ahead. So I'm proud of that fact. I'm sure there are other universities that were very good at this as well, but yes.
I think I can answer Katie's and Michael's questions together, maybe.
Sure.
So in terms of getting started in research and interdisciplinary work. Getting started in research, you can get started at the beginning of your freshman year if you want, if you find a good fit and you contact faculty. I've had students, undergraduates. Right now I have 3 undergraduate researchers working in my group. And one of them actually started in his first semester of freshman year. And so you can get started right away. You just need to contact faculty and meet with them and see whether it's a good fit. And yes, like there are definitely things you can do if you have time ahead of time to be able to contribute more. Coding, I think, is a big one. In most groups these days, even if you're doing hardware, you need to have some sort of coding background, and that can be very useful, whether that's MATLAB or nowadays most people work in Python. And so having a background in programming is not only going to help you get started in a research lab, but also is going to help you with your classes. I think actually in the first 2 classes you take, you actually get introduced to programming and coding at USC as well. So if you already know some coding beforehand, that would be helpful getting started. Regarding interdisciplinary work, I think one of the best ways is to get involved in a research group or a lab that works on the topic area that you're most interested in. Of course, beyond that, for example, one of my undergrads is actually not in electrical engineering, he's from biomedical engineering department. But beyond that, you can also take courses from different disciplines, different areas that are on topics that are interdisciplinary, that are interesting to you. And so one of the things that's great about USC and electrical and computer engineering specifically definitely falls into this category is that we actually have a very large and broad department. And so guaranteed, if there's some area under engineering that interests you, even if it's, you know, joined with biomedical engineering or physics or applied math, almost guaranteed there's at least one or probably multiple faculty that are working in that research area and that you can contact and work with. And most to my knowledge at least, most of the faculty are very receptive to undergraduate researchers and work quite often with undergraduates in their groups and their labs. And so hopefully, I don't know if Krishna or Ubli want to add anything to that, but.
Krishna, you want to say something?
No, I agree with everything that you said. Definitely, you can get involved as a freshman. You know, it's important to be resourceful, you know, and I agree learning, having some programming skills is important, but also just being flexible to learn what the needs are of a different research group. We have a program called the Merit Research Program in the Viterbi School that some students are offered that when they join. Even if you're not, you can earn your way into that within a year or so. I've had students that were not in that program, but then earned a spot after their first year, and that provides some monetary support for your involvement in research. And one thing I would say about getting involved in research, it relates to the first question that was asked, which is about what are some common challenges. And Constantine mentioned kind of time management, and I totally agree. You know, it's very common to, I've seen it happen many times where students come in and you just, you know, overachiever mentality, right? I want to do everything. I can do everything at the same time. And, you know, undoubtedly, everyone that comes in is incredibly capable and can do a lot at the same time. But pacing oneself is very important. And research is one of the things that is one of those things it's not easy to kind of swap in and swap out. Usually you need to have scheduled in some large blocks of time. So for those of you that are interested in doing in research, I would make sure you can calendar in like 4-hour blocks in your schedule, because it is really hard to multitask in research.
I love that idea and bringing up the word overachiever, because if there's one thing our admitted engineering students all tend to kind of have as a common denominator, it's an overachiever mindset. And so hence a lot of these questions are, how can I do everything right away? It's usually kind of the thread of these questions, at least through all the ones that we've had. And if I could add my 2 cents, there's a balance I think that's important. You don't go into college thinking you're going to do nothing but study, and you don't go into college thinking you're going to do everything. It's finding that limit for you as you go, and that's going to take some time. So just recognize you're not going to have it figured out when you start. But our faculty and our staff, as Dr. Mitra mentioned, we're all there to help you, and everybody struggles with some of those same things. The question that Micah's asking, I wanted to kind of expand upon and see if we can get some more insight on, the difference between electrical engineering, computer engineering. We have a degree program called electrical engineering with an emphasis in computer engineering. We have this joint program called computer engineering and computer science that some of our students in attendance have been admitted to, which is a joint kind of, it's jointly administered by the computer science department and electrical and computer engineering. Can we help explain how this all lays out and the nomenclature and how the curriculum's laid out with this hardware-software dynamic?
Well, I have to be honest, I think this is a little challenging to do. I suspect that most electrical engineering and electrical and computer engineering departments across the US have strong similarities. Some of this, to be honest, is some branding, but there are certainly computer engineering courses and areas of research, and we have significant strength in that. And that's one of the reasons why we are an ECE department. I talked about these sub areas before. Our department literally is divided into 3 parts: electrophysics, computer engineering, and systems. And given the significance of the computer part, we make computers, if you will. We design algorithms for them, etc. We felt it was important that our department and our degree reflected that diversity in terms of the research. And you will see that there are a number of departments that have done this name change over the years. So I think you should look at the institution and decide, does it have the programs and the research and the courses that you want, and not worry too much about the labeling of the department. It's really the programs and the resources and the faculty and the peers that you're going to experience that should define what place you choose. What is the place that has the best alignment for you?
That was very
The other thing is that there's not that much rigidity in terms of the courses that you can take. And so
we have a flexible program, it's true.
And so if you, and as Krishna mentioned at the beginning, especially in your 3rd and 4th years, you have a lot of freedom and flexibility to take courses and specialize in areas that interest you. And so regardless of whether for example, you might be just in the regular ECE program, electrical engineering, but you might be also really interested in computer science type stuff. So you're more than welcome to take CS classes as electives or computer engineering classes. So just because you've decided your degree to be in computer engineering or electrical engineering does not exclude you from being able to take specific courses that interest you, or even perhaps doing a minor in something else if you choose to do so. So as Ubli said, don't look so much at the label. Actually, look at the courses that are offered. You can all of the courses offered each semester are publicly available online. You can go and check, and for a lot of them, you can actually even download the syllabus and see what the course is about and what it has to offer. And that will help you determine whether what you're really interested in. And for a lot of you might not even really know what you're interested in. And so just seeing how many courses are available and how broad it is might also be helpful in that you have a lot of options. And you can, when you learn a little bit about each area, then you could specialize in your third and fourth years and really decide which areas you want to take advanced courses in and learn more about.
I saw a question on the progressive degree program. Paul, did you want to take on some of that, or?
You bet. Yeah, I can handle that really briefly. And this is something we handle definitely in our keynote session. So if you haven't attended our Viterbi school-wide keynote sessions, they happen on Tuesday. But the PDP program, progressive degree program, is combining your bachelor's and your master's in reduced time, and that's typically in 5 years. We say typically in 5 years because everybody is different. And so you're saying, is it possible to do it in 4? Yes, I've seen students do it in 4, but that is very case by case. It depends on the individual student, the individual undergraduate degree program, and the individual master's degree program, and exactly how you went through that curriculum. So there's always possibilities, but I always want to tell students to plan on that being a 5-year program, but that will be an advisement issue as you go through. No one is anywhere near us being able to predict anything with how you're going to deal with courses 3-4 years from now. So recognize we're going to help you. Students are doing it in reduced time, and we're going to help you figure that out on a case-by-case basis. So there's lots of possibilities.
I just want to throw in one thing, because I often teach these sort of intro core graduate courses, which means I usually have a handful of PDP students in my classes. And the one thing that I'll say is you might have a variety of reasons as to why you want to speed things through, but recognize that employers or other graduate schools are going to look at what it is you've studied and what you've accumulated. So there's not a way to get out of the learning that you have to do, right? And so if one of the strategies of getting through 4 years is to somehow cut corners on something, that could have negative consequences later. And, you know, life is long. There are going to be many opportunities to do lots of things. Learn as much as you can when you can, right? It gets much harder later on. You know, going back to school after you're working for a while, I think is actually quite challenging to do. Especially if there are financial issues. So again, I peddle, you know, a certain thing, which is that I'm very pro-education, and I think you should learn as much as and take as many classes as you can. This is the undergraduate university environment is totally primed for this all immersive education, right? And there's nothing like that ever again. Even grad school is very different from what you're going to experience as an undergrad, and it's unique and special. And you know, don't cut it short. It's really worth it.
I totally agree with Ubli, and from personal experience, I went fast and hard through grade school, and in college. In college, I took 5 years, and it was, you know, when you come to undergraduate degree programs, and if you choose to do graduate school, I think you'll find an immense amount of intellectual and personal freedom, right? And so it is a time when you really can explore a variety of areas. You can, you know, in my case, I took on additional majors. I spent 5 years for my undergrad, but I did a multiple major, right? And so I agree with what Ubli said. I couldn't endorse it anymore. I would recommend taking your time and trying to absorb as much as you can into your toolkit, right? This is the time when you bring it in, you fully integrate it, and you'll spend the rest of your life using it. And the more you bring in a very solid way, the more powerful you'll be for the rest of your career.
And taking the time to learn things properly, I think, rather than like if you can cram things, and it's not just about having time to take enough classes, because you can say, okay, I'm going to take 10 classes, or I mean, I'm exaggerating, but I can take all these classes at the same time. But then if you're cramming at the last minute because you don't have time to digest and learn the contents properly, then you're quickly going to forget everything. And later on, when you go on to take a job, or when you go to graduate school, or once you go on to the next thing, you're not going to properly learn things. And it's all of that, a lot of that material, you might have seen it, but it's still going to be confusing in your head. And I mean, a lot of concepts in engineering they require time, and they require like repetition and seeing it multiple times. And if you are just cramming a bunch of classes at the same time because you're trying to rush to get to the end, then I think you're going to miss out on a lot of that and on a deeper understanding of a lot of fundamental concepts.
Yeah, and I have to say, I lived that. I did my undergrad in 3 because I had a lot of AP classes. I did a 1.5-year master's degree. I went to work for 1.5 years. And my first year of my PhD was relearning everything again. And because of having worked, it was almost like it was a total reset. Now, this wasn't bad. I learned things really well. I'm not that bad at it. Obviously, they let me come here. But I wish I had spent more time at undergrad. You know, it's like folks who graduate early from high school. I talk to a lot of parents about this, and I say, you know, unfortunately, the only end game of doing these things early is you get to work a year or 2 longer than everybody else. And you know what? They call it work for a reason. So again, and try to enjoy this time, absorb as much as you can. It's magical, and it doesn't, I mean, I don't want to say that the future is bleak, because I quite enjoy my job, but each stage has its beautiful elements.
Well, that was perfect, and we've gone over our time, and we're not going to hit every question, but I appreciate all the questions that we got, and that was a fantastic note to end on. So I don't think there's anything better to say. And for all of our students that are out there, if you got more questions, you can email us. Our career stats are at viterbiadmission.usc.edu/beyond, and you know, always be in touch. These faculty, Dr. Mitra, Dr. Sideris, and Dr. Nayak, I mean, thank you so much for taking the time to talk to our students. I hope that they had as much fun as I did. This recording will be up on our YouTube page if you want to watch it in its entirety, and the audio will be one of our podcast episodes very, very shortly. So once again, thank you very much for joining us. I would love to stay on the faculty and catch up with you at the end, but when I close it, it's going to kick you all out. So I apologize. Thank you very much, everybody. Thank you very much.
Thank you so much.
See you all soon. Fight on, everybody.
Thank you for joining us.
And you're wondering if you can use it? Is that what you're saying? Yeah.
Come to USC.